Good day, this is Dr. Amudathaya, Associate Professor Tripoli from Rohini College of Engineering and Technology. We are discussing about the Power System Operation and Control course, and let us see about the low frequency control of a single area system, under which we are going to deal with the controlled case. The difference between the generated power and the instant load demand will cause changing of nominal system frequency at the normal state. If the amount of generated power is less than the demanded amount, then obviously the speed and the frequency of the generator units will begin to decrease and the vice versa. Hence, the amount of production of the synchronous generators is made sense for frequency deviations which are occurring in the system in order to maintain a balance. The frequency is normally varied by about 5% between the light load and the full load conditions. So while considering a change in load where it takes place between the two machines are running in parallel, then the change in load which is either at S1 or S2, and if the generation of S1 is alone regulated to adjust this change so as to have a constant frequency, the method of regulation is known as flat frequency regulation. The other way of sharing the change in load is that both S1 and S2 would regulate their generations, and this is known as parallel frequency regulation. The change in the particular area is taken care of by the generator in that area, thereby the tie line loading remains constant. This method of regulating the generation for keeping the constant frequency is known as flat tie line loading control. All the generators in such an area constitute a coherent group so that all the generators speed up and slow down together, maintaining their relative power angles would cause a control area. The boundaries of a control area will generally coincide with that of the individual electricity board company. So most AC motors which are run at speeds that are directly related to the frequency. The speed and the induced EMF may vary because of the change in frequency of the power circuit. When operating at frequencies below 49.5 Hz, sometimes the steam turbines and certain rotor will go under excessive vibrations, and the change in frequency may cause a maloperation of the power converters which may create the harmonics. And for power stations which are running in parallel, it is necessary that the frequency of the network should be maintained at constant level for maintaining the synchronization of the alternators. When many devices when connected to the grid will only work properly if the input frequency is within the specified range. So obviously if there is a change in frequency, it is globally economically optimum to keep the grid frequency within a smaller range unless and until it is going to cause a greater problem. The inductance of the inductive elements are chosen based upon the switching frequency. So this obviously causes a disturbance effectively. So the low frequency control of a single area system is nothing but it includes the combined structure of speed governor, turbine and the generator load models. All these models have been discussed in the earlier lectures. And for steady state analysis, we can say that under the steady state condition, the speed changer has a fixed setting, that is del PC is equal to 0, and the load demand changes. This is known as free governor operation. So del F is equal to 1 by D plus 1 by R into del PD, where Kp is nothing but 1 by D and D is equal to dou PD by dou F. Considering a step change in the speed governor system and the load demand when it remains constant. Here this is the case. Here del PD of S is equal to 0. So obviously del F is equal to 1 by D plus 1 by R into del PC. So this is the condition of a static analysis.